This video is on electron affinity. So we've just finished talking about ionization energy, which is defined as the energy required or needed to remove an electron. So we talked about the fact that if I have a neutral atom A, then I'm putting in energy to turn this into a cation and remove an electron. Okay, so my ionization energy values will always be positive because this is an endothermic process. Okay, so that's a review. And of course, we've talked about whether ionization energy is big or small, depends on distance from the nucleus and Zeph. But today, this is a different discussion. So the second part of this discussion is on something called electron affinity, which is defined as this. Okay, so electron affinity, or EA, is defined as the energy change. Note my choice of terms here, that's important, that occurs when an electron is added to a neutral atom. So for example, if we take the chlorine the chlorine atom, we give it an electron, it becomes the chlorine ion, and in this case, the electron affinity, we could look this up, is a negative value, which means energy was released. Okay, now that should make sense to you because chlorine is one electron away from having a complete octet or a full energy level. So chlorine would gladly accept an electron. In doing so, it releases a big amount of energy. So this is true for most atoms. Okay, keyword most. So most atoms do release energy when gaining an electron, and thus their electron affinity would be negative. But there are a few exceptions. Okay, so that's kind of what we want to talk about. So that would be where electron affinity is actually positive. Energy is not released. Okay, so if we look at our periodic table, that's kind of at the bottom of your note paper. I didn't write the whole thing. But I draw our attention to the fact that we were just talking about chlorine and fluorine. And if we look at your note paper, we see that all these values are negative. Oxygen, sulfur, selenium, they have negative electron affinities, even boron and carbon, even, contrary to what a lot of students think, the group 1, okay, almost everybody has a negative value, which means almost all atoms release energy when they gain an electron. But there are a few exceptions, which I have highlighted. The noble gases, nitrogen, and then beryllium and magnesium. So we want to talk about these 3 exceptions. Okay, so the first one is the noble gases. Well, we know that the noble gases already have 8 valence. They have a full level. And they're already stable. So they have no interest in gaining an electron, okay? They do not want to gain an electron. And so they actually will not release any energy with gaining an electron. You actually have to force the noble gas to gain an electron. And so because you're forcing it to gain an electron, what this means is that your electron affinity is going to be positive, because in this case, its energy is required. Okay, you're gonna make it take an electron. So that's opposite of what we think normally happens with things like chlorine, who says, yes, absolutely, I'd gladly take an electron and I'll release energy in the process because now I'm stable. So I think for the most part, the noble gases make sense as an exception. They're already stable. They do not want to gain. They will gain, but not willingly. You have to force them to gain. The other 2 are a little harder to understand. So the first one we'll do is beryllium and magnesium. So if we look at electron configurations, I'm just going to do 2s. It's 3s, sorry. This is beryllium, and this is magnesium. So while neither wants to truly gain an electron, because remember they form cations they want to lose, but making them or asking them to gain an electron would put an electron into a higher energy orbital, okay, because the 2p is higher in energy than the 2s, and the 3p is higher in energy than the 3s. So gaining an electron would put the electron into a higher energy orbital. That's not a stability situation. It has no interest in doing this. It's not good, so to speak. And so this doesn't occur naturally, okay? And instead, both beryllium and magnesium, you would have to force it. And then the electron affinity would also be positive for these two. Now, the question always comes up, well, how come it's not positive for calcium and strontium underneath? I don't really know the answer to that. I do know if you look at your chart, they are only very minorly negative, but I don't really have an answer for you as to why they also are not positive. Maybe it has to do with it's a bigger atom or something. I'm not sure. Okay, and then we only have one other exception to this, which is nitrogen. So I'm going to go underneath my table. This is something we talked about in the exceptions to ionization energy trends. So if we think about nitrogen, it also has a electron affinity that is positive. So if we look at, here's nitrogen, right? And so if we try to give nitrogen an electron, this is what should be, oh my goodness gracious, what you should be thinking about is the fact that this is a half-filled level, which we know brings some stability. Okay, so if we tried to give nitrogen an electron, it would break that stability, because now I have more than a half-filled level. Okay, so because we would lose the stability from the half-filled level, nitrogen says, I don't want to do this. It's not an energy releasing situation, and opposite of that, you would have to force nitrogen to gain the electron. So your electron affinity would be positive. So again, what we're thinking about a little bit is that electron affinities are going to be negative for the ones who release energy and will naturally gain an electron kind of on their own. So the few exceptions occur when they absolutely have no desire to gain an electron for reasons like it's a noble gas and already has a filled level, for reasons like a beryllium and magnesium, where you'd be putting an electron into a higher energy orbital, or for nitrogen, where you would be disrupting that stability that's already there from your half-filled level. I mean, in those cases, that process is not going to occur on its own. It's not going to release any energy at all. And in fact, to make it happen, you would have to force the atom to gain the electron by supplying it with energy. So ionization and energy and electron affinity are kind of opposite of each other, but not exactly. So we have to be really careful. Ionization energies are always positive. We wrote that at the top, because they involve the removing of an electron that's always attracted to the nucleus in some capacity. So thus energy is always required. Whereas electron affinity is talking about is energy released most of the time when an electron is added. But there are a few situations where that's not the case, and then electron affinity is positive. So most questions in AP are going to revolve around ionization energy, but it is possible that electron affinity comes up, and for that reason, we learn it and we learn to differentiate between the two.